Section 4.2, Basic Sine, Cosine, and Tangent Equations. So here's number one. It says find all real numbers that satisfy each equation. So we're looking at sine of x minus 1 equals 0. I'm going to rewrite it the following way. Sine of x equals 1. And in this equation, I need to look for all the x values that satisfy this equation. And in this case, it's going to be more than one value. Right away, you should recognize that pi over 2 is a solution to this equation, but that's not the only one. So to have a better understanding of all the solutions that we're going to have for this problem, let's look at this. I'm going to break this up. Let me get my pen. As two functions. This is going to be my first function, y sub 1, and this is going to be y sub 2, the 1. And I'm going to look at the graph of these two functions. And basically what I'm looking for to see where these two functions intersect. And notice that they intersect here, here, somewhere over here, an infinite amount of times to the right, an infinite amount of times to the left from this point. So all I'm going to do is describe all those solutions using the following, which is going to be x is equal to, which is the first answer that I choose to work with. I could have chosen negative 3 pi over 2, or I could have chosen the one to the right here of pi over 2, which is actually 5 pi over 2. And then I keep adding 2 pi units from that starting point. And to represent all of the answers, I need to use the notation of k, in which k is an element of z. And this is how you describe the solution to number 1. And actually, excuse me, solutions to number 1, because there are an infinite amount of solutions. The graph should help you see why there's an infinite amount of solutions. Here's number 2. So now we're looking at cosine of x minus 2 equals 0. Just like number 1, I am going to solve for cosine of x. This is what I get. I am going to need to look at the unit circle and determine what x values or what radian measures, angles, gave me 2 for cosine. And something should come to mind, but let's continue. So here's y sub 1. I'm going to let the y sub 1 equal cosine of x, y sub 2 equals 2, and I'm going to graph these two functions. Here's the cosine wave, and here's the horizontal line, y equals 2. And notice that these two functions do not intersect. And like I mentioned at the beginning of number 2, that something should have come up. Well, this is not cosine of angle is never going to be greater than 1, so that's why this is no solution. If you think of the unit circle, but also if you just look at the graph, these two functions never intersect. So this is the answer to number 2, no solution. Let's go to the next slide. So here's number 3, same directions. I work with I solve number 3 and I rewrite tangent of x is equal to radical 3. And then again, I'm going to work with the two functions. I'm going to graph them. So this is going to be my y sub 1, tangent of x, y sub 2, radical 3. We're familiar with graphing tangent of x. We're familiar with graphing radical 3, which is a horizontal line. And notice that this is where they intersect. Here, 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 and so forth. And they intersect an infinite amount of times. So what I'm going to do is I'm just going to describe this answer here first. If you look at the unit circle, you should recognize that that is pi over 3. And then from there on is every pi units. So to describe all solutions, the infinite amount of solutions that we have for this equation, I use k, in which k is an element of z. And this is my answer. Let's go to number 4. Now, it just changes slightly. It says final angles in degrees that satisfy each equation. So I'm going to solve for sine of x, which meant that I took away 3 and then divided by 2, and that's how I end up with sine of alpha is equal to negative radical 3 over 2. And then from here, you look at y sub 1 being sine of x, y sub 2 equaling the right-hand side. I graph these two functions. I get something that looks like this. Notice instead of using radian measures for the x values, now I'm using degrees, just to keep this in mind, that they're asking me to find all angles in degrees. So from here, notice that I have more solutions than the previous problems. So what I'm going to do, I'm going to describe the following. Notice that this is an answer. If you look at unit circle, sine is negative on the fourth quadrant. So, and that angle turns out to be 300 degrees. So this is 300 degrees, and this other solution here is related to this 300 degrees, and it's actually 360 degrees to the left of 300, and it hits this angle. So this solution set is describing all these points of intersection where the wave, sine wave, intersects the horizontal line as the sine wave is going up. If you read this from left to right, it is going up. It hits, crosses the horizontal line here. It's going up, and it crosses the horizontal line here. So this right here is describing, all these points of intersection. Now the next one is describing these other points of intersection, which is sine is negative also on the third quadrant, which is actually 240 degrees. And then 240 from here, the next set of answers will be 360 degrees to the right of 240 and 360 degrees to the left of 240. So, and this is the answer to number 4. It's just a little bit different, but you should be able to follow. Number 5, we're going to do this one in class. Let's look at number 6. So just like number 4, I'm going to isolate cosine of alpha, and this is what I get. From here, same process, I'm going to graph this. Y sub 1 is cosine of x, y sub 2 is going to be radical 2 over 2. Once I have these two functions, the cosine wave and the horizontal line, I notice that this is where they intersect. These points right here. So I'm going to describe first the answers in which the cosine wave is crossing the horizontal line as it's going down. So I'm describing these points of intersection. Once I describe this first point of intersection, which turns out to be 45 degrees, and if I just add 360 to the right of 45 and to the left of 45 an infinite amount of times, it gives me all these solutions. It describes all these solutions as the cosine wave hits the horizontal line going down. And then now I'm going to describe as the cosine wave is hitting the horizontal line going up, which is the one that I'm going to use as my starting point is 350 degrees, which is here. And then to the left of 350 degrees is right here, to the right, and so forth, by me using the following set notation. This describes all those answers. And here are the solutions to number 6. Let's go to the next slide. Here's 7 and 8. Those will be done in class. Let's look at number 9. So this is just slightly different. This problem's going over because this is going to be something you're going to be seeing in a future section. Some sort of formula. So what I need to do is basically I need to solve this equation, and notice that my variable is beta, which is an angle, which means that you should be thinking that we're gonna have to use the inverse function to find this angle. So I'm gonna isolate sine of beta once I multiply both sides by 52.9, 52.9 of the left side of the equation, the right hand side of the equation. This is what I get. And then at this point, I have sine of beta equals this, but I'm looking for beta, so I know I need to use my inverse function. And notice that I have beta prime, because once I do sine inverse of whatever this is, which is what you see inside these brackets, I end up with 35.4 degrees. Oh, I forgot to mention this. Change the mode to degrees. And notice that the problem, excuse me, let me erase that, is asking me to find a beta that is between 90 and 180. And if you remember reference angles, the way that I'm going to be able to give an answer that is between 90 and 180 using reference angle is going to be 180 minus beta prime. So it's 180 minus 35.4, and you end up with 144.6 as your answer, 144.6 degrees as your answer. I can clarify this a little bit more in class. Let's go to number 10. So another equation, you need to solve for you need to solve for alpha. So first you need to isolate cosine of alpha. It's going to take a little bit of algebra. Just rewrite this. What I did is I move all of this to the right hand side, to the left hand side, and then I move the 6.8 squared to the right hand side, and this is what I get. At this point, I'm going to divide both sides by by this. 2 times 3.2 times 4.6. Both sides. Once I do that, this is what I get. And I have cosine of alpha equals whatever this is. So since I'm looking for alpha, again, I'm going to have to use the inverse functions. So alpha is equal to cosine inverse of whatever this is. You punch it into the calculator, and you end up with 120.3. Now, in this case, I don't have to compensate because the alpha that I need has to be between 90 and 180. And if you remember, the way that inverse cosine behaves, it's always going to give you an angle that is in the first and the second quadrant. And I forgot to mention this earlier, but 9 sine inverse is only going to give you an angle in the first quadrant and on the fourth quadrant. And it's never going to give you an angle in the second quadrant, and that's where beta lies. This actually concludes the video.